Yeah, hello. Yes. So thanks so much for inviting me. It's very exciting to share some ideas with a different audience from the one I'm used to talk to, like neuroscience people. And so the main goal of the talk is to convince you that, so the takeaway to convince you that the brain is really an interesting model system to study spin glasses. So I've been very stressed about preparing this talk because it's kind of like a completely different thing, a topic from what I usually talk about. I've been thinking about this problem of glassy dynamics since I switched from theoretical physics to neuroscience 15 years ago. This has been a chip on my shoulder that I always wanted to figure out, and I think I finally did. This talk is going to be extreme work in progress. So I'm 85% sure of what I'm going to tell you, but I'm still not super convinced. But I just wanted to put it out there and get feedback from you guys because I'm not at all a spin glass expert, and so the goal here is to start a conversation. And so first I wanted to mention about my lab. So I'm at University of Oregon in Eugene, where we have a neuro AI center. So this is a new kind of like topic at the intersection between neuroscience and artificial intelligence. That's what we do. And we do workshops for trainees and so on. So this is my lab, and the work I'm going to talk about today is mainly part of a long-term collaboration with Merav Stern, who's a Rockefeller, and a bunch of other people. So first of all, in my lab, there's so many topics that the couplings between trainees is frustrated, and so there's kind of like some kind of glassy dynamics in the behavior because we talk about a lot of different things. So the main focus of the lab is doing brain-computer interfaces. So it's a theory lab. We collaborate with experimentalists where we develop brain-computer interfaces to control behavior in monkeys and humans. We study neural dynamics or large-scale circuits. We study naturalistic behavior. What are the complex systems that can capture naturalistic behavior? And we study multitasking using AI system and decision-making and animal models. But today, again, I'm going to talk about something that has nothing to do with what we do in the lab, which is glassy dynamics. And the outline of the talk is I'm going to give you a kind of like a long introduction about recurrent neural networks, because I assume that there's probably very, very few neuroscientists in the audience, maybe a couple. And so I'll try to show you what kind of data we deal with. And then I'm going to get into the physics of these spin glasses. And please interrupt me at any moment to ask questions. So this project was motivated. I have to acknowledge Gianluigi Mongillo, who's a collaborator in Paris, who, when I first switched to neuroscience, he just put this, worm in my head of, yes, so there's kind of like glassy dynamics somewhere in the brain. We have to figure it out. This was 15 years ago. And then Gianluigi wrote a few papers that you see listed here, which have been extremely influential in motivating me and thinking about this. And my motivation was, can we have a system, like a model that is expressive enough to capture brain dynamics that we want, and still analytically tractable with mean field methods, so that we can study it and have fun with it. And so we wrote a few papers on the topic with Merav. These are some of them, and with a group in Italy, in Padua, which is a group in statistical physics. It's just to advertise some of the results. So here's what we're going to talk about. So I'm going to show you two kinds of recordings that we can do from the brain that people use in the field. So the first kind is extracellular recordings, where we lower electrodes in cortex. Here you see an electrode lowered in cortex. These are the neurons. We record electrical activity around the electrode. And then we do what's called spike sorting, which is high-pass filtering and identification of events. And we identify around the electrodes single neurons from the shape of the spike they emit, the action potentials. We can sort them, and then we can study the spiking activity of simultaneously recorded neurons, which nowadays I show you 4, but nowadays the technology is like exploding, and we can record from tens of thousands of neurons simultaneously, electrically in this way. So this is like amazing new developments. A different way to record from the brain is to use calcium imaging, where we genetically modify neurons to become fluorescent where they are active, and then we can image them. This is a mouse brain from the top, and you can see the vasculature and everything, and we can measure their fluorescence and then extract the activity from there. And I wanted to show you a video of a recent experiment by the Vaziri lab at Rockefeller, just to give you like the idea of, so where they do the image, the whole brain with some light sheet microscopy. It's like a phenomenal technique. Here you can barely see, okay, there's like 35,000 neurons simultaneously recorded from all areas in the brain. There's like 1 million neurons, I guess, in the mouse brain, something like that. So they can record up to 200 or 500,000 neurons simultaneously recorded. And, that's the volumetric imaging. And so basically, yeah, so this is what we have to make sense of. And, it looks like a spin glass. So or less. So the rest of it, yes.
You have different Z stacks?
Yeah. So, okay, so there's several timescales here. The timescale of the Z stack is super fast. It's like milliseconds. And the timescale of the calcium indicator is slower. So it has like an intrinsic, a rise and decay time, which is about in the order of a few hundred milliseconds. And so the activity that I'm showing here, as you see, seconds go very fast. So this is sped up. And here is the motion energy of the face of the animal, because you can decode the facial movements from this activity.
By the calcium, not by
the calcium imaging is the main problem. Yes, and so they're developing faster and faster calcium indicators now. Like it's called GCAMP8F now, I guess, that has a transient that's about 100 milliseconds. So a decay constant, and so that's progressing. Every month there's a new.
Well, and the voltage indicators.
So that's a different thing. So this is calcium imaging I'm showing you. There's also voltage imaging. That's a much more powerful technique. That's much faster because there's no decay in that indicator. There's like a super fast decay in that indicator. People are developing that now. There's the first few papers appeared last year, I think, which are more convincing, where you can also measure directly the voltage of the membrane potential of a single cell. That's the gold, the gold standard, if you want to call it, of what we would like to have as theorists. Yes.
But you can't scan as many cells.
No. Yes. So there's a trade.
I mean, just the comment because of question of time. So, one of the difficulties is we can do very high-level processing things in 100 milliseconds, right? And so, in some extent, and the mouse presumably can too, maybe even faster. And so, certainly, some of the processing is, which is maybe some of the ones one can most hope to understand because it involves neurons and your feedback and so on, is not possible to see with these methods.
Yes, I agree. Yeah, so there's various ways of getting around that. From calcium, you deconvolve the signal, for example. What you really want to see is the spikes, because the neurons, talk with each other with spikes. So that's a challenge with imaging to detect spikes. So, these are all things that we think about. Data, like the signal processing part is very difficult, and also the interpretation. But, this is just a cartoon to get you interested in, okay, so this is the data. Not only that, but in fact, we have the dream come true here, where we can measure the JIJ, the coupling metrics, has been calculated, inferred from data where, they took a millimeter square of mouse visual cortex and they scanned it with EM reconstruction. They reconstructed the whole tissue and they could reconstruct the JIJ matrix, which is the coupling between postsynaptic and presynaptic neurons. So we do have the matrix that we can study. And so we have activity, we have the connectivity, we can study the statistics of the connectivity, such as the reciprocity in the coupling, which is what we really care about here, right? And we found a huge excess reciprocity in the coupling, which points toward,
You have signed things, Fields law, or is it just unsigned?
So we know the cell types, so we can, infer the sign if you want to. So this is the topology, if you want, but there's also, you have the strength, which is the size of this synaptic spine, and you have the sign because for some cells, you have the cell type. So, this is like a breakthrough. There's 1 millimeter square. In the Drosophila, they have mapped the whole brain for a few flies. And so this is happening right now. So that's why I'm very excited about this, because we can study really the dynamics here. And so you can study the topology, right? So the excess reciprocity and the degree distribution of the connectivity. And so in this recent paper with the group with Samir Shrivais, Amos Maritain, we use this we studied this with a neural network. Maybe we'll discuss it tomorrow in the discussion session. This is just, advertisement. So, all right. So, what do? Well, ideally we have spikes, and Sarasota talked about this yesterday, right? So this is just a one-on-one what we do. Well, we have spikes, but usually we really want to deal with rates, with continuous variables. So what we do? Well, we just convolve the spikes with the postsynaptic current kernel, and we get a low-pass filter of this. That's a continuous variable, xi, if you want. And then what do? Well, we build up a network, a recurrent neural network, where we, wire up together these with neurons, with directed couplings, and the variables we think about are these currents, these postsynaptic currents, and we just couple them with some coupling matrix. For example, the one that I showed you yesterday in the previous slide. And then we need to choose this transfer function. That's the function that turns input currents into firing rates, the output of the input-output function. And it could be, any sigmoid or whatever, ReLU, like people do, whatever. For this talk, I'll choose a tan H because it's easier, because it's odd, and that's similar to spins, soft spins. But there's many different ways to do it. And then depending on the Jij, the whole business of dynamics starts. And so, for example, these are 4 examples of dynamical regimes that you can have in these networks, depending on the structure in the Jij. Again, this is like a whole neuroscience course in 3 slides. So you're welcome to come talk to me later. So we have linear regimes that can lead to limit cycles, for example, oscillations, something like that. Or single attractors, kind of like a single attractor with linear response around it. Or we have very nonlinear regimes. What are nonlinear regimes? Where you can have multiple attractors, where you switch between the attractors. Or you can have chaotic dynamics. And so these are kind of like more interesting from a theory point of view. And let me give you a few examples. So Sarah yesterday talked about this, and Pier Francesco also talked about this. Well, the simplest case of a nonlinear dynamics is attractor dynamics, where this is the equation, of the network. We choose the Jijs with a very special form that's called the Hopfield network, where they're symmetric and low rank. So they have rank P, and they're bilinear in these vectors. Those are the memories. And if you initialize the network, you end up in the closest memory. So that's the Hopfield network. And so activity converges in an attractor. And, 40 years ago, Amit and collaborators solved the full phase diagram of this network as a function of the temperature that you can add here as white noise, and function of the memory load, which is how many of these memories you store. And what they found is that if you have low temperature and low memory load, the memories are global minima. But if you increase the memory load, the memories become local minima, and new minima appears here. In fact, an exponential number of minima appears that are a spin glass. And so this model is kind of like the prototypical case of a spin glass in neuroscience. And if you increase memory load or temperature, then the memories become maxima, so or saddle points, so they're not retrievable anymore, and you only have glassy states. And if you increase memory load or temperature even more, you get into this phase with no retrieval at all. So, this is being kind of like in the back of everybody's mind that there's glassy dynamics, but that's okay. That's because we have symmetric couplings here. And so okay. So something else we can do is, if we relax this idea of symmetric couplings, for example, if you take the Jijs to be completely random, then what we have is chaos. So we have chaotic dynamics here. time translation invariant chaotic dynamics that's captured by an autocorrelation function. So this is the autocorrelation function of a chaotic system. All neurons have the same time scale, and you develop this chaotic dynamics. In the case where JIJs are, again, they have zero correlation, and they have there's a transition to chaos where their variance is larger than a critical value. And what the cool thing you can do in these networks, which is the work of Chaim Sompolinsky from the 80s, is to study all of this using dynamic mean field theory for glasses, if you want. And so you can reduce this network into a single site dynamic mean field, which is so this is eta is the mean field. And the cool thing about, the technical complexity here is that the mean field is self-consistent. So the autocorrelation of the mean field is the autocorrelation of the whole network. So you have to solve these self-consistent equations, which is where all of the physics come from. So it's different from the usual p-spin story. So it's a bit more complicated because you have this self-consistency that gets into the game, and the object is the autocorrelation function. All right, and so, well, it turns out the connection here is that these are very high dimensional systems. So very recently people have computed the complexity of these systems, for example, and they show that they're like exponential in the number of neurons. And so it's a high dimensional landscape. So it's very fun to think about. So in my lab, we've been studying a slight change. Yes.
What does complexity mean in this context?
Yeah, if you can hold on for 3 slides, I'll define it later. Yes, I get to that in a second. In my lab, we've been studying a slight modification to this Sompolinsky model, the original Sompolinsky model, and let me show you what it is. So this was motivated by actual data, where in many cortical areas we found this structure. So we look at, so this is, for example, for mouse auditory cortex. So what I'm showing you here is a raster plot of 131 neurons, and these dots are where they meet the spike in time. So you can see this is called a spike raster with all the simultaneously recorded activity of all these neurons. So you can study the covariance matrix of these neurons, and what you find is that they are arranged in clusters. So there's very strong neural clusters or neural assemblies where neurons within the cluster are very correlated with each other. And so we wrote a series of papers where we kind of wanted to go from this idea of clusters into like a different kind of models of different level of technical complication that could capture this cluster dynamics. And so what we do is that we now model not single neurons, but clusters of neurons. So we introduce the idea of a network of clusters. So these are like populations now, where now the xi's in our network, you can think about them as the average activity of neurons in the same cluster, which are very correlated, if you want. And then we have effective couplings between the clusters. These are the off-diagonal values in this matrix, for example. And the extra ingredient to introduce is now once you go into this population discussion, population framework, you have to introduce a new term in the equation, which is a self-coupling. So this is a coupling of a neuron I with itself with a certain parameter that represents the size of the cluster. This is very hand-wavy, but you can show that this is, you can make this rigorous from spiking microscopic spiking models like the ones that Sarah talked about yesterday. You can do a mean field version and see that this is the kind of equation that you get.
So this is, S can be either sign, depending on the cluster.
So yeah, S is a parameter, right? So it can be either sign. In our case, it's positive because it's the size of the cluster. And I'm only going to talk about positive S, although it's interesting to study about negative S too, but I'm not going to think about it because it's not part of this framework. And so what do we do now? Well, we have a model with essentially 2 parameters. We have the cluster size, and that I take to be the same for all clusters for today, but although we studied multiple sizes, that's super interesting too. This is a positive real parameter. And then we have this coupling matrix. So the coupling matrix, we take it to be IID. So there's no correlation in the couplings. Okay, so this is apparently not Glassy, right? Because these are completely random couplings with no correlation. And okay, so this is the model that we've been thinking about with Merav. And what I'm going to talk about today is the dynamics of this model. And I'm going to show you that, in fact, it has Glassy dynamics, which was extremely surprising. Well, we'll see how far I can go. But the idea is that there's a Glassy landscape of marginal states, exponentially many of them. The model has aging, shows aging. There's a phase transition to aging. And the model shows rejuvenation also. And we can study all these things using dynamic mean field theory. So that's kind of like the general gist to take away, even if I'm not going to get there probably. All right, so this is the model. Again, there's two parameters, the self-coupling and the variance of the J's. So the variance of the J's is the usual variance that people think about when they think about disorder. And so we'll think about this phase diagram in the G and S plane. And so let me mention now why this model is interesting. So what you would do if you wanted to study glasses, and this is what basically Valentina's talk from yesterday, you would not have a self-coupling. You would have an equation like this, like that's the standard equation of a recurrent neural network if you want. And you would introduce correlation in the couplings. So this is what you would do. If you have a correlation in the coupling that's this gamma parameter that's equal to 1, so there's full symmetry, then this is a glass. It's kind of like a soft version of Sherrington-Kirkpatrick, if you want. Then you can take gamma less than 1, right? And you can look at the dynamic mean field equations. And what you do get in the single site here is what's called the Onsager term. So this is the term that couples the response function to the activity of each neuron, right? And it's proportional to the symmetry, degree of partial symmetry in the couplings. So it turns out that if you do this, you actually have to use you have to work with the two sides, so with cavity, and you get a very complicated set of dynamic mean field equations, which are numerically very hard to solve. So this is what we did with the group in Padua. And so what I thought was that, well, what's really the essence here? What's the essence of this term, this Onsager term that drives Glassy dynamics? Is it the non-Markovianity, the fact that we have this, we have to have a long memory? Or is it really just the fact that we have a self-interaction? And so what we can do is we can say, well, okay, let's just take the response function to be a delta function, right? And so this turns into a self-coupling, and we lose the non-Markovianity of it. And it turns out, actually, that this is sufficient to generate Glassy dynamics. Yes?
If gamma is not 1, so it's not symmetric, I think that this is not Glassy, it's chaotic.
Yes, thank you. So that's an open question, right? So is it Glassy for gamma less than 1? We've been thinking about it. Valentina has also been thinking about it. We figured out we're looking at the same question. And so it has some properties of glasses, and it's still open to see if it traps or not.
This question actually was investigated some time ago by Kurshan, and we had a paper with Samantha on some models on this. And what you can show is that as soon as the asymmetry is there, you get a positive Lyapunov exponent. So there are models where you can compute the Lyapunov exponent. It's always positive as soon as gamma is less than 1.
Okay, thank you. So I need to read the paper. I was not aware of that.
Kind of separation of time scale when gamma is close to 1, so that you have a first time scale where you basically see aging, but then this is interrupted by the drive, the asymmetric drive.
Okay, super interesting. So I would like to know more about it. So I'm not going to talk about this model because I'm going to just drop this, and I'm going to only study the single site model with the self-coupling. And so this is the summary of the talk, is this phase diagram. So in the plane where we modulate the gain or the variance here of the random couplings here on the x-axis, and the strength of the positive self-coupling on the y-axis, we have several different phases. And so we have a first phase here for small values of the parameter where the network is silent. So you just initialize to any initial condition, and then it just decays to 0. So that's a fixed point attractor at 0 value.
I guess I'm now
Yes.
confused after the previous discussion. This is, the J's are still independent, or it's now symmetric?
So there is no correlation in the J's in this model.
Yeah.
There's only a self-coupling.
So it's very far away from
Very far away from that region. Yes. And so and it's much easier to study because we don't have this Onsager term, if you want, which complicates very much the physics. Well, the calculations. So what's the phase diagram here? Again, silent here. So this is the standard structure of networks that was studied by Sompolinsky et al. So if we increase the gain, there's a transition to chaos at g equals 1. That's the standard transition to chaos in recurrent neural networks from the 80s, where activity becomes chaotic. That's what I told you about at the beginning of the talk. So, but when we increase the self-coupling, a bunch of cool things happen. So first of all, there's a phase transition where a complexity becomes positive. So here, complexity is 0 in this chaotic region. By complexity, I mean the number of stable states, not just fixed points, but stable states. So here there's no stable states, there's just chaos. But there's a phase transition where complexity becomes positive, and an exponential number of states appear. And so above this region, some interesting things happen because there's a second phase transition, I would claim, where you start to see aging and trapping. And this occurs for much larger self-couplings. And so in this region, if you have a finite network, the network has this exponential number of stable states. So in finite network simulations, eventually you will get to fixed points. And these fixed points have a very interesting structure that I will mention. All right, so okay, then I'll go fast here. So we calculate the complexity. The complexity was already defined by Valentina yesterday. It's the same object, and so you take the fixed point equation, the Jacobian, and you impose that there's a stability on the states that you find. So this is the structure of the stable states. So what I'm plotting in green here is the force function that we set to 0. We set this is a static solution, so we set it equal to a Gaussian, self-consistent Gaussian field. This is static, right? It's a Gaussian distribution, the self-consistent with the activity, and so you get that the points are going to be concentrated in these two regions, and they're bistable. So the fixed points are such that neurons are really like pushed to saturate the tan H at +1 or -1. So there's two branches in this fixed point structure, and in fact, even the dynamics look bistable. So this is one particular neuron that I simulate a positive self-coupling, and you see that the network becomes really bistable. So there's like a switching between these quasi-stable states. So it's a super interesting dynamics that occur in this regime. Okay, so you can just turn the crank. We really studied Valentina's paper for this, and so you can compute the complexity. And what you find is that above this critical line here, again for self-couplings larger than 1 plus change, you get a positive complexity. So you can do two calculations of complexity. You can compute the quench complexity or the anneal complexity. And so here for this plot, I showed the anneal complexity, and I suspect that the quench one has no replica symmetry breaking, and it's equivalent to the anneal, but this is still work in progress that we're trying to finish. And so this is the anneal complexity here that I showed. This is the color map is the value of the anneal complexity that's above this particular transition line here, and it's positive, and you have an exponential number of states. So now the question is, are the states marginal or gapped? Is their largest eigenvalue 0 or negative. And so what we can do is we can then compute the anneal complexity condition on the stability of the states. And what we find here is that, so this is the stability level. Here we have marginal states. And as you go to the left side of the plot, you get more and more gapped. So this R value is 1 plus the largest eigenvalue of the Jacobian of a state. And what we find is that the complexity is monotonically increasing as we reach the marginal boundary. And in fact, that's the maximum of the anneal complexity at the maximal, at the marginal boundary. So the most numerous states are the marginal ones. So that's takeaway number one. Okay, so second thing I want to show you is that I think there is aging in the system, and I would be happy to chat about it because I'm not a super expert on this, so you can tell me. So what we look for now to study aging is a breaking of time translation invariance. So we can study the two-time autocorrelation function of the network. So this is, phi of x is the activity. We take the autocorrelation function. And so the idea is that if you have time translation invariance, the autocorrelation function is depends only on the difference between the two times. But what we found is that that's not the case. And so what we found is that there's a breaking of time translation invariant. And there's a scaling exponent that captures this two-time autocorrelation function. And so this happens above a second phase transition here. So you have to go and study the system for large value of the self-couplings. And so there's a technical problem here that arises, which is the fact that in finite simulations, you eventually reach a fixed point if you have finite n. One of these bistable fixed points. The time to reach a fixed point here on the y-axis increases exponentially with the number of neurons, with the size of the network. So this is really hard to think about aging in the finite network. In fact, you can't really study that. So what you can do, which is the statement that if you take n to infinity and the aging time very large, these two limits don't commute. So yeah, of course. Yeah, sorry, I'm saying obvious things, but I figured this out recently. Yes. So what you can do is you can do dynamic mean field theory. So you first study the n equals infinity limit of the network, where you turn this network into a single site equation that's self-consistent, where the mean field has the same autocorrelation as the activity, right? And so these are the two equations that you have to solve to study this limit. And we're going to look at the two-time autocorrelation function, which is our order parameter here. And so this is what we find. If you scan the S and G plane and you run this dynamic mean field for a very, very long time, you find this autocorrelation function. So this is the profile of an autocorrelation function calculated at aging time TW, where TW goes, becomes later and later from blue to yellow. And you see the typical kind of like a structure that you find in aging, where there's this slowing down of the autocorrelation function. And you can rescale time and find that all these autocorrelation functions in the TW divided by tau variable all scale with the same, can be rescaled with the same exponent. That's approximately 2/3. So it's sub-aging, if you want. Aging with the standard, simple aging would be mu equals 1. Here you find mu equals 2/3. I'm not sure what that means. But what we can do is we can ask, what is it that drives aging in this network? And so, yes.
Which limit, n first or t first?
Yeah, so this is dynamic. So this is the dynamic mean field, this picture of the network dynamics. So it's an infinite n, and then we take tau TW very, very large. So it's the standard mean field aging, if you want. So what is it that drives aging? So this is what I'm still not super sure, so what I'm working on. So the idea is that, you have this force here in brown. That's the force that I showed you. Well, the equation, the velocity of the network x dot, if you want. And what happens is that you can look at the distribution of velocities of the networks of the network. This would be this curve here, phi prime, if you want. And so the idea is that this distribution of phi prime, as you age, kind of like depletes from here and get this distribution of phi prime gets concentrated at 0, which is driven by the fact that the units are progressively getting stuck at these bistable wells that I showed you. So at the beginning, there's a lot of neurons whose activity is in between, and a few neurons that are stuck at their pinned down in the two potential wells, the bistable solution. And as time goes by, you deplete the reservoir of units that still have dynamics, and progressively all of the units get more and more stuck. So this is the what we call the movers. So this is the fraction of the movers at the beginning of the simulation of the DMFT, if you want, and the fraction of the movers with progressive aging at 2 times. You see that the fraction of the movers depletes and units get stuck progressively at the 2 bistable units. And this procedure never ends, so has a power law scaling. So you kind of like deplete more and more and more and more, and that's what drives aging. So this is, if you want, the log-log plot of this phi prime, which is this distribution of movers that becomes more and more and more depleted. So this is kind of like what we have in mind as a mechanism for driving aging. And what you can actually show is that, well, you can study the Jacobian of different aging times, and you see that so I'm not super sure about this, but I'm trying to finish this, is that you approach aging on the marginal manifold. So you have this marginal manifold of exponentially large number of marginal states that have 0 eigenvalue, and you approach asymptotically, you approach this marginal manifold. So the movers move from positive exponents to more and more to an exponent that's closer and closer to 0. So with this 2/3 exponent, yes.
I guess the reason of the 2/3.
I don't know. That's the outstanding question. Is I don't know. So So this is really I have no idea why.
If you could get the same 2/3 if you change the phi from hyperbolic tangent to another function.
I don't know. I haven't looked at that. That's a good question. Well, if you change the phi, things are going to get much more complicated, because if you take a positive phi, for example, that's in Valentina's talk yesterday, then you get kind of like silent or activity, like the silent neurons, a fraction of silent neurons becomes like another parameter, and that the equations become much more complicated. So I haven't been able to think about that very much. But yeah, that's a great question. So this is where things stand. And what's really fun is that you can also show rejuvenation. What you can do is you can now take the network and add a shock. What's a shock here? Well, that's an external magnetic field, if you want, with an amplitude that you can choose. What's a shock in the brain? Well, that's an external stimulus that's delivered to the network. This is a neural circuit, right? So we just present the stimulus. And so what you see is that what I'm showing you here, this is the flip, what I call the flip fraction. So it's a fraction of neurons that flip. So the movers, what I mentioned before as the movers. So here, very, very late in aging here, I apply a magnetic field for like a pulse, like a very short pulse. And then what you see with these curves is that I partially reverse aging, depending on the strength of the magnetic field, which is this color code here. And then the network starts to age again. And so this is like this usual rejuvenation. And okay, of course, this is done with a dynamic mean field. So this is the rejuvenation with dynamic mean field. So this looked kind of fun from a neuroscience point of view, because it gives you ideas on how to study this in the brain in terms of autonomous dynamics versus stimulus delivery, and so on. And of course, I wanted to mention again Gianluigi Mongillo, the instigator for this. So he studied this kind of like a high complexity glassy landscape in more biologically plausible networks where you have inhibitory neurons and you have symmetric couplings. And so you actually, so in these networks, it's much harder to do computations, calculations. And so, so he gave evidence for this glassy dynamics in these more biologically realistic networks. All right, so this is the summary. So again, this is our phase diagram where we have like a transition to positive complexity of the stable states that are marginal states. And you have these periods of transient chaos where you finally settle, but then there's a phase transition to a period with a scaling law where you deplete the movers asymptotically. So that's the claim, and you have rejuvenation. And so these are, if you're interested in this, so tomorrow we can have. I wanted to see if we could have a discussion on, more brain-related topics. So how do we measure? How do we test for glassy dynamics in the brain? What are kind of like things that are experiments that people are thinking about? And again, I want to acknowledge Merav, who's a long-term collaborator on all dynamic mean field projects. And yeah, that's it. Thank you. Yes.
This is a bit more of a comment that could open your next section tomorrow, but follows directly from what Francesco was saying. If I understand correctly, when this GIG are generically asymmetric, what some political and other prove that Crisant is that you go into chaos very, very easily, probably for any infinitesimal perturbation, actually. But what I find very thought-provoking, what you're saying, is that, well, the Sompolinsky original model is that O2O connected thin glass, but often if you take neuromorphic inspiration, there is actually structure. There could be a self-interaction. The other one that is even more banal is that you could have two types of neurons, excited and inhibitory. And recently, Julia Garcia-Lorenzana in the audience and others studied what happens in that case when you have a structured neuroreciprocity. And you can actually save aging in that case. So you can bypass that problem of Sompolinsky. But you have these oscillations. So you have an Edwards-Anderson parameter that oscillates. So this seems to me that would be interesting to see, to sort of consider, maybe with an eye towards neuroscience, the structured neuroreciprocity, whether it's because there's a bipartite structure in inhibitory and excitatory neurons, or some more realistic clusters that you extract and see in the regime of extreme neuroreciprocity, how much you can save of spin glass dynamics.
So that's a great idea. So people have studied this kind of non-reciprocity. For example, this big J matrix, you can take it with block structure.
Yes, exactly.
With different variances in different blocks.
Yes.
So these were papers by Merav like about 5 or 6 years ago, and they find a super complicated phase structure there. They didn't study glassy dynamics. They studied transition to chaos depending on this, and timescales depending on that. So you can do dynamic mean field theory with this block structure that's been done, and it's a super interesting random matrix problem, actually. So that would be wonderful.
And my claim is that can go around the problem. That is another mechanism to go around the problem that's generic to avoiding chaos, which is something that... Because when it's chaotic, then you kill aging.
Yeah, of course.
Right? And the question is, how do you rescue it?
Yes. Okay, cool. Yeah, we should think about it more. Yes.
One question, because you show from an anatomical point of view that actually the support to the GIJ is rather symmetric, right?
Yeah.
But now, what about the values of the GIJ? I guess obviously that's very tough to compute or measure in any way. But
yes. So what we looked at is, so this is called the microns data set. So this is called the microns data set, and what I'm showing you here is the topology, basically the adjacency matrix. We did not look at the actual value of the value of the weights. That could be inferred from the spine volume, but there's technical problems with it. And so this is the excess reciprocity compared to Erdős-Rényi, if you want. So you can measure it like that. And so in the model that we did, we introduced degree connectivity in the topology and then correlation in the value of the weights. So it's a heterogeneous dynamic mean field where the weight matrix is a product of the adjacency times the value, and we can do technically that's because we can do the quenched average separately on the two. But in practice, I don't know in the microns data how reliable the measure of the value would be, but it's there. So you can actually look at that. I don't think that people have really looked at that very much, but typically it would be, so what people expect is a log normal distribution of values for, for excitatory E to E, and for all of them, E to E, I to I, excitatory inhibitory connectivity, it typically look normal, I would say.
Yeah, but maybe you could extract the gamma parameter.
You could extract the gamma parameter from the values. Yes, I think, yeah, I think you could do it. Yes, yeah. The errors are, so the problem with the microns data is that there's 100,000 neurons, but only 1,000 of them have been proofread. So it's tricky how to interpret it. And for the values, you have to look at the volume of the spines, which is very difficult to assess from using machine learning, basically. So, but that's a wonderful problem to study. Yes. Yes.
But beyond the exact value of the connection, you said you have access at least to the cell type.
Yes.
Can you divide that excess reciprocity into excess reciprocal connection between neurons of the same type, and then that would give you a sort of a positive gamma from the excess reciprocity between opposite types, and then that would actually give you like anti-correlation?
Yes. So the question for those who didn't hear is, do you know the cell type here? And the answer is yes. So for some of these neurons, we know the cell type, so we can actually condition the connectivity on the actual excitatory inhibitory neuron, or even the inhibitory cell type. So they have somatostatin, VIP, PV neurons, so different cell types of inhibitory neurons with where you can study the actual preferred connectivity between cell types and then condition all these parameters on that. So that's a fantastic idea. It's not been done, I think, and so it would be really super cool to check.
Do you know at least if there's more like reciprocal connection between same type or different type?
No, I didn't look at that at all, but that's a great question. Yeah.
Any other questions? No? Okay, so let's thank you.
Thank you.